Say that we have a random variable x comes from a normal distribution with unknown mean mu and known variance sigma squared. Say that we have collected n samples from the distribution of x and thus also have a mean of our sample. Using this mean, there are two ways to estimate mu. We can perform a hypothesis test based on a guess, or we can formulate a confidence interval for mu. The first approach we will talk about is hypothesis testing. We start this method by making a claim as to what we think the value of mu is. Call our estimate mu naught. Then we assume it is the true value of mu. Based on this assumption, we find an interval such that a sample mean observed outside of it would be unlikely enough to engender doubt in our claim that mu naught is a true mean. The definition of what unlikely means, or the threshold of likeliness past which we doubt that mu naught is a true mean, is up to us. We call this the significance level. Because our samples were independently sampled from the same identical probability distribution, by the central limit, we know that their means distance from the true mean relative to the sample standard deviation follows a standard normal distribution. So since we're assuming mu naught is a true mean, we can use a z-table to find our confidence interval. If our selected significance level is alpha, alpha is equal to the probability of x bar minus mu naught divided by the sample standard deviation being less than negative z of alpha over 2, or x bar minus mu naught over the sample standard deviation being greater than z of a over alpha over 2, z of alpha over 2, or by the definition of the probability of complementary events, 1 minus alpha is equal to the probability that x bar minus mu naught over the sample standard deviation is between negative z of alpha over 2 and positive z of alpha over 2. We can rearrange this to isolate x bar in the middle, and then from this get a confidence interval. The equation tells us that any sample mean is in this confidence interval 100% of the time if mu naught was a true mean of the distribution the sample came from. Consequently, if mu naught were the true mean, the probability of us observing a sample mean outside of this confidence interval would be alpha. If this is unacceptable for us, then we can reject the claim that mu naught is a true mean. So if our observed sample mean is in the confidence interval, we fail to reject the null hypothesis that mu naught is a true mean. If it is outside the confidence interval, we reject the null hypothesis that mu naught is equal to mu. As discussed earlier, x bar minus the true mean over the standard deviation follows a standard normal distribution. Unlike the hypothesis testing method, instead of making an initial guess at what the true mean is, we leave it in symbolic notation as mu. Then we construct a 95% confidence interval for the normalized difference of the sample mean from the true mean. Because as we said, x bar minus the true mean mu. Because as we said, x bar minus the true mean mu divided by the sample standard deviation follows the standard normal distribution, we can use z-table values to construct our confidence intervals. So we have that in 0.95 is the probability of x bar minus mu divided by the sample standard deviation falling between negative z of 0.025 and positive z of 0.025. Rearranging this, we can get a 95% confidence interval for just mu instead. There's an important connection between the second approach using confidence intervals and the first approach using hypothesis testing. And that is that calculating a confidence interval can help to quickly evaluate the result of a hypothesis test. More specifically, if we are performing a hypothesis test with alpha 0.05 and our estimate for mu is mu naught, if mu naught is in the 95% confidence interval for mu, then we fail to reject the null hypothesis of the test that mu naught is a true mean. The rationale behind this is that for us to fail to reject the null hypothesis, the sample mean we observed must have been inside the 95% confidence interval for sample means for samples from a normal distribution with mu naught as its mean. Thus mathematically, this can be noted as our observed x bar being in between u minus and plus z of 0.025 times the sample standard deviation. Subtracting by x bar and flipping the signs, we can rearrange so that mu naught is in the middle. This expression shows us that an equivalent condition for us to fail to reject the null hypothesis is for mu naught to be in between x bar, our observed x bar, plus our observed bar minus and plus z of 0.025 times the sample standard deviation. However, these bounds for mu naught are the same bounds that we saw from the 95% confidence interval for mu. Thus, in a hypothesis test where alpha value selected is 5%, we fail to reject the null hypothesis if and only if our hypothesized estimate for mu naught is in the 95% confidence interval for mu. This is a relationship between confidence intervals and hypothesis testing.